So what sort of correlators of the symmetric orbifolds we are trying to calculate, and so the idea is these correlation functions. So this is a 2D CFT, and it lives in what I will call the X space. So that's the space on which it lives. So the correlation functions will be something like, and maybe I denote by V the twisted sector ground states corresponding, say, to the W1, and it'll sit at X1, and W2 sitting at X2, and Wn sitting at Xn. So here are the points, the x's on the, so this is the X space, this is a sphere, this is the sphere on which our 2D CFT lives, and we want to calculate these correlators. And the idea of how to calculate them is to think of them as lifting them from some Z space. A Z space can in general be a Riemann surface of higher genus, but in this lecture today I'll focus on the case, I'm only looking at a contribution where the Z space is also a sphere. So this is the genus 0 contribution. There can be higher genus contributions, but today I'll just focus on those. And we're looking at maps gamma of Z that lift, that have then the corresponding number of points here. So these are the xi's, x1, x2, up to xn, and these will have z1, z2, up to zn. And we're going to lift them by undoing this twist by w, and the condition is that the map gamma of z must be holomorphic, and it must have the property it maps to xi plus ai times z minus zi to the wi for z in the neighborhood of zi. That's the covering map condition. Okay, to get a sense of what this looks like, so let's look at a simple example. So for example, let's look at a 3-point function of 3. Let's put them at 0, 1, and infinity. And so how could that correlator be non-trivial? Well, so remember, these are going to be three-cycle permutations. And in order for the correlator to be non-trivial, the product of three-cycle permutations has to be the identity. So for example, one configuration could be that I take this to be the representative corresponding to the permutation 1, 2, 3. This one I'll take to be 3, 2, 4. And this one I'll take to be 1, 2, 3. Sorry, I'm doing it wrong. So this should be, so this should be 1, 2, 3. This should be 3, 2, 4. And this should be 3, 4, 1.
So the 3 to 4. So you have at least 4 points, or how did, or is
yes. So I mean this. So n is sort of infinity, right? I have always as many n's I have available, and what you see is you can't do this just by involving 3 copies. You will need some of the additional copies to be involved. But what I'm saying is there is a product of three cycles. That's the identity. And because you see 1 gets to 2, 2 goes to 4, 4 goes to 1, 2 goes to 3, 3 goes to 2, 3 goes to 1, 1 goes to 3, 4 goes to 3, 3 goes to 4. So this is the identity.
Well, it could have been 1 to 3, all of them, right? The product of 1 to 3 times is 1 for
that would have also worked, indeed. Yes. In this example, that would have also worked. Yes. So this is the correlator. That is a correlator that is a covering surface from here to here. And what would then? So this is a configuration of permutation, so that the product is the identity. And what would the corresponding covering surface look like? Well, the corresponding covering map in this context would simply be the function z to the 4 minus 2z to the 3 divided by 1 minus 2z. So if you look at this function, you see near z equal to 0, how does this function go? This function goes at near 0. It goes like z to the 4 minus 2z. So it goes like, it goes like minus 2z3 over 1. So it goes like minus 2z3 plus higher order for z near to 0. So this is of this desired form. Right? Because it maps as 0 to 0, and then near 1, sorry, near 1, it'll look like 1 minus 2 times z minus 1 cubed. That's what it does near 1. So it maps 1 to 1, but again with a threefold covering. And then if you want to understand what it does at infinity, you should look at the inverse of 1, gamma to the minus 1 and evaluate it at 1 over u, and take u to 0, and then you can see that this goes like minus 2u3 for u near 0. So this is an example of such a covering map, right? It's a map that is holomorphic from the sphere to the sphere, but it has a threefold covering near the special points 0, 1, and infinity, and it has no other critical points. I mean, it's 1 to 1 everywhere else locally, but at 3 points, 1, 2, 3, namely 0, 1, and infinity, it has a threefold covering.
And this W is the length of this cycle, yes?
Yes, the W is the length of the cycle. So this is sort of the baby example you should have in mind. And as I said, we are going to look today at the case of genus 0. There are in general higher genus versions that we may need. So as I explained to you last time, what this should mean is that the corresponding CFT correlator, the corresponding worldsheet correlator, so what we expect is that the corresponding vertex operator will come from the spectrally spectrally flowed sector corresponding to V1, and it'll be a vertex operator that will depend on x1 and on z1. And I'll explain how to define this vertex operator in a second. And what I argued that the result up there would be naturally reproduced from the worldsheet if this correlator was a sum over covering maps. So if I fix a specific covering map, then it would just be this covering map. So this will go like the sum over covering maps. Then there will be some constant, and then it should go like a delta function for Zi. Zi should be constrained to be compatible with the condition with the existence of the covering map. So there are three basic things I want to explain to you today. First of all, I want to explain what I mean by this. Why is there going to be a delta function here, and how many delta functions do I get? So this is at the moment a bit vague, and I'm about to explain to you what precisely I mean by that. Then secondly, I want to explain to you how we define these vertex operators on the worldsheet. And then thirdly, I want to explain to you how you can prove on the worldsheet that this property is true. So let's start by explaining why covering maps are constrained. Why should there be delta functions? And this has to do with some relatively easy observation. So if there is a covering map, gamma, from the sphere to the sphere with branching points wi, then the Riemann-Hurwitz formula tells you that the order of the covering map, the number of pre-images of each point, is equal to 1 plus the sum from 1 to n, wi minus 1 over 2. That's the order of the covering map gamma from the sphere to the sphere. But if you think about this, so what this means is that the covering map will be a ratio of polynomials of degree n.
What is capital N in this context?
So in this, well, you mean in this
equation?
context?
In this equation.
Oh, so this n has nothing to do with that n, I'm afraid. This is yet another n.
What is it?
So this is the order of the covering map. I mean, it's the number of... So if I ask a regular point here, how many pre-images does it have here?
I see.
That's what n is. And it follows from Riemann-Hurwitz that once you specify... I mean, this depends on the genus. That's the genus 0 version. So once you specify it's a genus 0 covering of genus 0 with these branching indices, then Riemann-Hurwitz tells you what the order of this function is. And what this means is that gamma of z is a ratio of polynomials, and I'm going to write it in this slightly funny form. I'm going to write it as minus p minus of z over p plus of z, and p plus minus of z will be polynomials of degree n.
Should we call it with a different letter, maybe?
It's just in the Riemann-Hurwitz literature, that number is always called n. But maybe I call this, you see, this n virtually never appears.
Okay.
So let's call this number m, if that makes you happy.
Okay, whatever.
Because that n will basically never, that is always taken to infinity. So this will be polynomials of degree n, because then there are n pre-images. So what does this mean? So if I write down the most general polynomial of this form, there are 2 times n plus 1 coefficients. Each polynomial has a n plus 1 coefficients. So there are in total 2 times n plus 1 coefficients. Obviously, because I'm dividing them by one another, the overall scale doesn't matter. So the number of free coefficients, which is 2n plus 1, is the number of coefficients that this ansatz will have. On the other hand, I can ask how many equations do I have to satisfy for this to be a covering map? And when is this a covering map? You see, in writing it in this fashion, I can say the covering map condition is that p minus of z plus xi of p plus of z is equal to order z minus zi to the wi. Because you see, if I plug in, so what this means, p minus of z is minus xi p plus of z plus some high order polynomial. So if I plug this in here, this term will just cancel it. So this will mean near z equal to zi, this will just be xi plus order z minus zi. So these are the conditions I have to solve. So these are all the conditions. And I can ask how many conditions do I have? Well, how many conditions do I have? Well, I have n points. So I have n1 equals to n wi conditions. Right? So this is the structure of the problem. So these are the number of coefficients. And these are the number of conditions I have to satisfy. Yes?
Why wi?
Well, because it has to be of order wi, right? So that,
yeah.
Right? It's a polynomial, so there's the constant term, the first order term. So there are wi conditions at each zi. So this is true at z near zi. So there are sum over 1 to n wi conditions. But because of Riemann-Hurwitz, you see the number of conditions. So Riemann-Hurwitz tells me the number of conditions is sum over wi, but if I solve this, what is this? This is 2n. So sum over wi minus 1 is equal to 2n minus 1, 2n minus 2. And then what is this? This is the sum over wi minus n is equal to 2n minus 2. Right? So the sum over the wi is equal to 2n plus n minus 2. That's the number of conditions I have to solve. But if you compare this, so this is the number of conditions, and this is the number of coefficients. So you see, this is an over-constrained problem. I have for n, okay, for n equals to 3, I have exactly as many conditions as coefficients, so I'll be fine. But if n is bigger than 3, I'm going to have more conditions than coefficients, which means that generically there will not be a solution. So what this means is the number of conditions minus the coefficients is equal to n minus 3. Right? It's this number minus this number. It's 2n plus n minus 2 minus 2n plus 1. So it's n minus 3, so this would tell you that you only expect the covering map to exist on a space of codimension n minus 3. And that's the reason why we're going to get these delta functions here. The delta functions just explain to you the locus of the zi where the covering map will exist. And this is going to be a space of codimension n minus 3. And why is this important? Because you know, when you do the modular integral in string theory, when you integrate over the insertion points here, you have to integrate over all zi's, but you have the Möbius symmetry, so the Möbius symmetry reduces the integral by 3, so you're going to have to do exactly n minus 3 integrals, and you're going to get exactly n minus 3 delta functions from the conditions that a covering map exists. So this will exactly turn this modular integral that I wrote into into a finite sum, namely the sum over all the covering space contributions. Yes?
I mean, isn't it true that if you give the data, the combinatorial data of the permutations, then this actually determines the Riemann surface?
Yes.
So then there is not, why are we discussing it then?
You see, it fixes the ZIs, basically.
That's what I'm saying. So we don't need all this explanation.
Well, but I mean, what you want to think of this as, I mean, you can ask, I mean, what I'm trying to explain to you is if I gave you also the ZIs, then generically you wouldn't find a solution. So you...
What I'm saying is that if you know the X's
right.
and all the permutations, then you know all the Z's already.
Right,
so
except...
you're done.
Right, up to Möbius transformation, right? So that's another way of saying it. Okay. Yeah. But I mean, what this is telling you is that this fixes the ZIs completely up to the Möbius transformation of the covering surface. And therefore, when you do the integral over all the ZIs, you're just going to get a finite sum from the contributions of the covering surface.
Maybe just a remark. So there you assume that the points are at finite places because
yes.
Your example is kind of in contradiction.
Okay. So, but I mean, it doesn't really, I think infinite, yeah.
Point at infinity.
Yes. So this is done for the assumption that they're all at finite places, but because of the Möbius symmetry, that doesn't really matter, right? You can.
So the degree now doesn't quite fit that thing.
Right. So you have to be, but I mean, this is the generic version. Yes. So this is the reason why you're going to get a delta function, and you're going to get a delta function that will reduce the modular integral over the z's to a sum over the covering surface. Okay, so this is the first point I wanted to explain. So the second point I want to explain is how are we going to define these vertex operators? And this is a subtle point, and this is something that I think has been missed entirely in the previous literature, and that's the reason why people, when they were calculating the correlation functions of this SL2R by Sumino-Witten model, they really weren't calculating the right thing. So what do I mean by that? So remember, so the state corresponding to the twisted to the W sector to the ground state of the W cycle twisted sector will be a certain state that lives in the sigma to the W sigma. That's what we said. We said in the W twisted sector, the W twisted sector comes from the W spectrally flowed sector on the worldsheet. And we are familiar with the fact that how the Z dependence of a vertex operator depends on the state. So one way of saying this is that we can say if you put the state at 0, then the vertex operator at Z is simply determined by conjugation with the translation operator on the worldsheet. So if we know this, if we know the state field correspondence in conformal field theory, then it tells you a vertex operator at arbitrary position Z by simply taking the vertex operator at 0 and translating it by the translation operator on the 2D CFT, moving it to the position Z. So this is the canonical way in which a vertex operator depends on Z. Now we want our vertex operator also depend on X. And remember, X is the coordinate in the dual 2D CFT. So because it's also a 2D CFT, we also know how this should depend on X. Namely, it must depend on e to the x times L minus 1 spacetime, e to the minus x L minus 1 spacetime, right? Because it's a conformal field theory. So that's the way the conformal field theory depends on the insertion coordinate. And therefore, with respect to the target space, you do exactly the same thing. It is translated by the translation operator with respect to the Möbius group of the target space. But the L minus 1 of the target space is j plus 3. So this is equal to e to the x j plus 0 e to the z L minus 1 v of phi of sigma of w 0, 0 e to the minus z L minus 1 e to the minus x j plus 0. So that's how we're going to define this vertex operator. So you're probably saying, so what's the big deal? That's pretty obvious. That's clearly the right way of doing it. I hope that's what I've convinced you of. But this has profound consequences for the structure of the operator product coefficients. And it really is, it's important to understand so that we understand how to calculate these correlation functions. So you see, this hasn't, because, so remember how our symplectic bosons transform under spectral flow. The symplectic bosons transform under spectral flow in that their mode number is shifted up and down by W. So remember that sigma plus and minus, sigma to the W of psi plus and minus of n is psi plus and minus of n minus plus W over 2. That's how we said the spectral flow acts on the symplectic boson. So I can ask, how does the field psi plus of z behave next to the vertex operator corresponding to the state in the W spectrally flowed sector? So if I look at this, I can ask, actually I'm going to want to call this zeta. So I need to work out this OPE to understand the structure of these correlation functions, right? The structure of these correlation functions will ultimately be determined by using the Ward identities with the symplectic boson. So I have to understand what's the OPE when I bring the symplectic boson close to this vertex operator. Now this just has a mode expansion as psi plus of r, zeta minus r minus a half.
Well, why do you call it zeta now?
Well, because I'm going to introduce the z variable for the coordinate of the vertex operator. So this is the z variable of the symplectic boson, and I just don't want to call it also z, right? I need more.
And all this is on this.
This is on the worldsheet now.
On the dual theory, though.
No, this is not on the worldsheet, right? So these are the vertex operators in the worldsheet theory, right? So up to here, that was dual CFT. Now I'm going back to the worldsheet. And I'm trying to understand what does the worldsheet operator look like that corresponds to the insertion at x in the dual CFT.
And the worldsheet is the same by chance as this covering space.
Yes. But that I don't know yet. But
yeah, that will be the result.
That's what we are going to hopefully see. And on this worldsheet, what I'm trying to understand is the OPE of the symplectic bosons with these spectrally flowed states. And you see, I mean, you know how this works, so simply plug in this formula. So this tells you this goes like psi to the minus r minus a half. And then I apply the mode psi plus r on the state in the spectrally flowed sector. 0 and 0. And then this is the same thing as sigma w of psi plus r acting on phi in the spectrally flowed sector. Right? And this is the same as psi plus, according to the formula, r minus w over 2. And I'm going to look at the case w odd. W even is slightly more complicated, but it doesn't really matter. But just for simplicity, let's treat w odd, so that these fields live in the Neveu-Schwarz sector, then I don't have branch cuts. And then, so we are going to see that the leading term here, the lowest term that survives, is the term with r equals to w over 2. So the leading, the first non-trivial term, I mean, put differently, the terms that survive are those where r is less or equal than w over 2, right? The zero mode acts non-trivially because these states, remember, live in this Riemann sector representation where the zero modes of the symplectic bosons act non-trivially, but the positive modes kill. So if r is bigger than w over 2, then this is obviously 0. So this sum restricts itself to r less or equal than w over 2. And therefore, if I write down the leading behavior of this OPE, it will look like so this is a little bit technical, but it's important to understand this clearly because this will be the key to understand this localization property. So this will go like, so the leading term is r is equal to w over 2, so this will go like psi to the minus w plus 1 over 2 times the correlator, where this is psi plus 0 acting on phi sigma w 0, 0 plus higher order terms. That will be the leading term.
Zeta, right?
Sorry, zeta, yes. Yes, thank you. So the OPE of psi plus with this will go like zeta to the minus w plus 1 over 2. And that comes from the spectral flow, right? And it's more singular than you would have thought because you've spectrally flowed it, and therefore it's not the highest weight state. Now here I've evaluated that at x at 0, 0. Now what would happen if I moved it by z and I moved it by j plus 0? Well, if I move it by j plus 0, nothing happens, because j plus 0 commutes with psi plus. Remember, j plus 0, j plus is basically proportional to psi plus eta plus, and psi plus eta plus both commute with psi plus. So this just goes through. So if I had evaluated this at x and z, the only thing that would have differed is that I have a zeta minus, this is still right. I haven't written the, so this z, this would have become a z minus zeta to the minus r minus a half, zeta minus z. And therefore this would have simply, and here we would have had x and z, and then I would have simply had here x and z, and this would have become a zeta minus z. Right? There's nothing more complicated happening than you just translate everything. So instead of depending this on zeta, it depends now on zeta minus z. So that's what happens for psi plus. Now what happens for psi minus? So let's do the same calculation for phi minus. And I apologize for this being a little bit pedestrian. So I write down the same sum. Well, let's be a little bit quicker. So this is zeta minus z, zeta minus, well, let's put it at z, that doesn't matter. Zeta minus z to the minus r minus a half v, and now I have to move this in, and now inside this bracket I have to evaluate sigma w of psi minus. So this will become psi minus of r plus w over 2 on phi, sigma w 0 z, right? This is what I get when I evaluate this OPE. And now, which terms contribute? Now the terms that contribute are those where r is less or equal than minus w over 2. Right? Because this mode number must be 0 or negative. So this will go as zeta minus z to the minus, to the w minus 1 over 2 times this correlator plus higher order terms. Okay, so this is all pretty pedestrian, but now comes the crucial point. So this is true if I evaluate it at x equal to 0. Now what happens if I evaluate it at x not equal to 0? If I evaluate it at x not equal to 0, you see what this amounts to is that I have to put here an e to the x j plus 0, right? And I have to put the e to the minus x j plus 0 here, because the dependence on x is given by the translation operator by e to the x j plus 0 and e to the minus x j plus 0. But you see, when you move psi minus past e to the x j plus 0, they don't commute. So this is equal to e to the x j plus 0 psi minus of zeta minus x psi plus of zeta. Right? Because you see, j plus 0 is psi plus eta plus, and there's a non-trivial commutator of the psi minus with the eta plus, and it brings down the power of psi plus. So when I move the psi minus of zeta field past the e to the x j plus 0, I pick up a term that's proportional to minus x psi plus zeta. So therefore, this is, so if I evaluate this at x, then this isn't the only term, because I get this correction term. So this is the term that comes from the psi minus, but in addition I get a term that goes like minus x times psi, the OP of psi plus, and the OP of psi plus goes as such. So it goes like minus x times zeta minus z to the minus w plus 1 over 2 times this vertex operator plus higher order terms from here. Is that clear? That's the crucial point. The crucial point is that naively you would think that the psi minus OPE is highly regular, and that is true if you evaluate it at x equal to 0, but if you evaluate it for non-trivial x, you get a term that's proportional to x, and that's proportional to the OPE involving psi plus, which has a pole. So the OPE behavior of the symplectic bosons near these vertex operators depends on the value of x in a very crucial manner. I mean, if x is equal to 0, it's highly regular, and if x is not equal to 0, you get a term that's highly singular. And that allows you now to constrain the correlation functions of these fields and basically solve them completely. See the structure of these correlation functions. So the idea is that we are going to look at correlators, which I'm going to suggestively call P minus and plus, or P plus and minus of Z. Or maybe I should call them, well, actually I can call them Z. And I'm going to define them by saying that they are equal to, they're going to be equal to the product of I is equal to 1 to n, let's call them functions of zeta minus zi to the wi plus 1 over 2 times the correlator of psi plus minus of zeta with the product I is equal to 1 to n of these vertex operators. Now, there's a small subtlety here, which is again something that unfortunately is a subtlety of string theory. So the subtlety of string theory is because we're doing here superstring theory, you have to actually introduce something called picture-changing operators. And the picture-changing operators manifest themselves by the fact that you have to introduce in another number of n minus 2 W fields. These W fields are really not doing anything interesting. They're vacua with respect to the SL2R, but you need them to soak up some background charge. I don't want to explain it in detail, so this is picture changing, and this is one of the dirty little corners of superstring theory. This is something that happens in the superstring case, but not in the bosonic case. And the only thing you need to know about these fields is that they behave like the vacuum with respect to SL2R, but psi plus and psi minus have a 0 when they get close to WU alpha. So the WU alphas are
what is this P plus minus?
Yeah, these are functions I'm defining, right? They're defined to be the correlator of the correlator I'm interested in with the insertion of the symplectic boson field, right? I mean, this is the correlation function I want to calculate. And I'm simply inserting here this symplectic boson field, and I put in some prefactor here for a reason that you'll see in a second.
You multiply these two expressions.
Yes, and this is the multiplier. So P minus plus is defined by the expression on the right-hand side. And the only thing I want to say is that these W fields, they behave, so the J plus minus Z, I mean, they are in the SL2R vacuum representation. They're the SL2R vacuum state. And if you look at them with respect to psi plus minus of zeta, W of U, they go like a simple pole of sort order zeta minus U. That's the only thing I need about them. And they come from picture changing, so it's a bit of a complicated story. I don't really want to get into it. I hope you can just sort of think of this as being part of the sort of folklore of string theory. But it's important because I need to divide out these common zeros. So there's a sum going up to n minus 2 of zeta minus U alpha. Alpha is equal to 1 to n minus 2. So this is just from this picture change.
U alpha was what?
U alpha are the insertion points where you introduce these picture chaining operators, but they drop out at the end. It doesn't matter where you sit. Yeah, so this is something when you calculate these superstring correlators, you have to do this. It's not just the correlator, there is something you have to change the picture, absorb the charge, and that's the effect of it. So I'm defining these correlation functions, and morally they're just the correlation functions of the fields I'm interested in with these symplectic bosons. And I've multiplied them with this prefactor, and what's the motivation for multiplying them with this prefactor? You see, this prefactor guarantees that this function doesn't have any poles. Because you see, as a function of zeta, it'll have poles at zeta equal to zi, but the poles at order zeta equal to zi are all proportional to minus w plus 1 over 2, and I'm simply multiplying with w plus 1 over 2 to remove the pole. So this term guarantees that this function doesn't have any pole. So the p plus minus have no poles. And they are therefore polynomials. Right? So they are therefore polynomials in zeta.
And why did you introduce this psi plus minus in the correlators?
Well, I mean, you're trying to derive the word identities of your correlator, right? So the way you define, so you want to calculate the correlator without the psi plus minus. But in order to derive the word identities, you consider the correlator where you insert the field, and then you get constraints. That's how you define word identities for affine, for current algebras, and here I'm doing the analogous thing here, and inserting these fields here.
So these are not physical correlation functions.
No, these are not physical correlation functions. At the end of the day, I'm interested in the correlator where this field is not present. But at an intermediate stage, I'm looking at those to get constraints on the correlator without those. And but think about what these functions are. So they don't have any poles, because this factor removes all the poles in the zi's. And so they are polynomials. So what is the order of the polynomial? Well, the order of the polynomial is, I have a sum from I is equal to 1 to n to wi plus 1 over 2. Then I have so I'm thinking of this, what's the behavior for zeta going to infinity? Then I have to subtract minus n minus 2. That comes from the 1 over zeta behavior. And then I have to ask, how does this correlator fall off when zeta goes to infinity? And because this is a spin-a-half field, it will fall off as zeta to the minus 1. So that's the order of the polynomial that's defined by this formula. And that's true for both p plus and p minus. But you see, when you look at this...
But why do you know it's polynomials? Weren't they supposed to be delta functions?
Say again?
Weren't they supposed to be even delta functions?
Well, I mean, as a function of zeta, this is, I mean, if you work out the correlator, you would just subtract out all the poles, and, I mean, the usual way you can calculate correlation functions in CFT, you would subtract out all the poles of zeta at any of the other points, and then you would use the fact that it's a meromorphic function in zeta, and because this doesn't have any, the poles are corrected by this. So once I've multiplied through it by this, it must be a...
So the correlators are supposed to be rational functions always, or meromorphic functions.
I mean, you know that the correlators, as a function of zeta, there must be meromorphic functions. Because you see, this is a mode expansion of this form, right? And then you just plug through the modes, and you do the usual contour arguments in CFT to see that this is a rational function as a function of zeta. And because I removed the poles, after I've removed the poles, it must be a polynomial of zeta. And I can calculate its order, its degree, because I can just read off how this behaves for zeta large. So this tells me how it behaves for zeta large, and then this factor goes like zeta to the minus 1, and the rest doesn't depend on zeta. But if you look at this formula, I mean, what you recognize is that this is just 1 plus the sum I is equal to 1 to n to wi minus 1 over 2. So this is just the degree of the covering map. Right? So remember when I said the covering map, I could write as minus p minus of zeta over p plus of zeta, where both p minus and p plus were polynomials of this degree. And what was the condition? Remember, that was how I counted the parameters for getting the covering map. And what was the conditions? The conditions were that p minus of that, p minus of zeta plus xi p plus of zeta has to go like the order of z minus of zeta minus zi to the wi, right? That was the way I characterized the covering map. I said it had to be a ratio of polynomials, and these two polynomials had to satisfy all of these conditions. But these correlators, once I've decorated them with these prefactors, are exactly polynomials of the right degree. They have exactly the degree that I know from the Riemann-Horwitz formula to be the correct degree. And what is the identity that they satisfy? Well, you see, we can just insert it here. You see, from this calculation of the xi minus correlator, you see that p minus of zeta plus xi p plus of zeta You see, this is exactly this term. This is the term that comes from the xi plus term. So this goes like this prefactor. So this will go like the product of I is equal to, this will go like the relevant piece of this prefactor, which is zeta minus zi, to the wi plus 1 over 2, times the term that comes from the remaining piece of the psi minus correlator, which is a zeta minus zi to the wi minus over 2. Right? So because of this OPE, you see this OPE, these were the terms that came directly from psi minus, these were the terms that came from psi plus. This piece subtracts out exactly this contribution, because you see the pi plus correlator is the correlator where I have psi plus instead of psi minus. So that subtracts out this piece, so then the leading term comes from here, and this leading term has to be multiplied with the leading power from here, and what I see is that this goes like zeta minus zi to the wi. So what this tells you is that these correlation functions, these polynomials, are in fact the polynomials that appear in the definition of the covering map. These polynomials define for you the covering map because they are polynomials of the right degree that satisfy exactly the correct condition. So you can extract the covering map directly from the CFT by considering the correlators with the insertion of the symplectic boson fields. The worldsheet theory knows about the covering map. It spits out for you the polynomial p minus and p plus that defines the covering map. But you know the covering map doesn't generically exist. So what this means was that somewhere this argument goes, so you see, if the zi's are such that the covering map doesn't exist, then there can't be such a polynomial. I know that it doesn't exist. So what must go wrong, and you can argue this more precisely, is that these two correlation functions must separately vanish. The only way around to this argument is that p minus and p plus are identically 0, and that's the argument that tells you that they are actually localized at the positions where the covering map exists. I mean, the argument is sort of, if they exist, you can extract the covering map from them. But you know that the covering map only exists if the zi sit at special positions, and therefore the correlators can only be non-zero when the covering map exists. And you can argue this a bit more. So here we are looking at these correlators. Then you can show that if the correlators with the insertion of psi plus and psi minus are identically 0, then already the original correlators also have to be identically 0. And from them you can read off that the correlation functions have to have this delta function property that I mentioned. So this is sort of the CFT, the honest worldsheet CFT way of seeing that these correlators have this remarkable localization property because they give rise to the polynomials that define the covering map, but you know that these polynomials can't generically exist because the covering map doesn't generically exist.
Does it mean that those vertex operators V, they don't have a free field realization? Or do they?
You mean you mean these?
Yes.
Well, I mean, it's a little bit subtle, right? I mean, they're the Riemann sector, but spectrally flowed. And as you see, all of this comes from the spectral flow. So somehow, after spectral flow, I don't know how to write it in terms of an exponential of free fields anymore. But it's up to spectral flow, it's a totally free field calculation, right? It's a free field calculation, except spectral flow somehow does something magic so that these correlators have this remarkable delta function localization property, and therefore you can't, this vertex operator you probably can't write as exponential of free fields, because if you could, you would never get out this delta function.
Yeah, that's right, or whatever, like at least for me, maybe it's just a limitation of my imagination. I don't quite know, right, how such a result would emerge from some analytic expression.
Right, so I suspect there is no simple free field realization directly for these vertex operators, but as I explained to you, the Riemann sector is just the standard Riemann sector, right? And the only thing I've done is spectrally flowed. So apparently that's enough to introduce this subtlety, and you see why it is, because it leads to this X dependence, it leads to all of these properties. So it is free field, but you can't just easily calculate it by writing down exponentials of free fields and doing big contractions. There must be something more subtle, and I wish there was this is something we haven't yet understood. This is a roundabout argument of explaining what the answer is. You would like to have a more hands-on way of just calculating it.
But maybe the other thing is that if we were on flat space, this would not be the same vertex operators, because those are in Fourier space, right? And this is in position space somehow, right?
So the same vertex operator as what?
This V of Z. I don't know. So X is a kind of position in space-time, right?
Right. X is the position in space-time, and Z is the position on the world sheet.
In usual string theory, we do Fourier transforms, and we put the vertex operator exponential of momentum times free field.
Right, right. So here we are sort of in position.
There one should kind of do Fourier transform, and then this could introduce delta function even in the...
Right, but obviously here it's a bit more delicate because we are not living on flat space, we are living on, the axes live on the Riemann sphere. So, anyway.
What I'm saying is that even in the flat case we would have...
I see, you're saying out of free fields you can still get delta functions of sort. But the delta functions here are sort of not quite the overall momentum conservation type delta functions, right? They're delta functions that link these variables to these variables in a way that... Yeah, so I wish I had a more... Look, it's made many people fall asleep to explain you this argument. It's a little bit a contrived argument. It's the best we have at the moment, but it's an argument that shows you that these correlation functions have this property. Now, the challenge is for everybody to find a more hands-on way of seeing this result. I'm saying you there's an argument that shows you that's the result, but I wish I had a more direct way of calculating this correlate. And I'm sure eventually we'll find one, but we haven't yet found it. But the key point is that it gives you this delta function property, and therefore, by the argument I explained at the end of the last talk, that essentially manifestly makes sure that the world sheet reproduces the structure of the symmetric orbifold correlators, because it localizes on the covering maps, you get the sum over the covering maps. And you can generalize this argument to higher genus. It works the same way in higher genus, and so you see the structure emerging, but at this moment in time, it's not as explicit as we may wish it to be, given the fact that we say it's a free field theory. It's a free field theory that you can't just calculate by big contractions, and that's a consequence of this funny spectral flow that somehow does something slightly novel, and we don't exactly know how to keep track of it. Yeah, so I'm basically running out of time, so I think I really want us to end by saying, you see, what this tells you is that the correlation functions, actually what you find is that psi minus of zeta plus gamma of zeta times psi plus of zeta inside this, that's a consequence of this these correlators are equal to 0, and what this looks like is you want to think of this as being an incidence relation in twistor space.
Oh, why is it 0?
Well, that's basically, this is basically this current, right? This is this relation, and because this is everywhere 0, you can show that this correlator is actually equal to 0. This correlator, you see, if near Z, for zeta going to Z, then gamma of zeta will go to X. So therefore, this term doesn't have any poles, and this is an analytic function that doesn't have any poles whatsoever, and therefore it must be 0. So this correlator is identically 0, and what this tells you is that this is really a way of explaining the space-time coordinate as the ratio of two worldsheet fields. And that's sort of the typical way space-time emerges in twistor space. In twistor space, you have the twistor variables, and the space-time coordinates is determined by an incidence relation that twistor variable 1 plus space-time coordinates times twistor variable 2 is equal to 0. So the way we want to think about this is that the psi plus and psi minus are really the twistor variables of the 2D space-time of our dual CFT, and that's an incidence relation, and that's the way the CFT discovers the space-time coordinate by virtue of this incidence relation. And that suggests that was the key insight that made us realize how to generalize it to AdS5 cross S5. Because for AdS5 cross S5, what you do is you write down the corresponding twistor fields, and you expect a similar relation. And that suggests for you what the worldsheet theory should be that describes AdS5 cross S5. And in fact, what it is, it's basically a theory where you have twice as many symplectic bosons, twice as many free fermions, and the T4 has gone. And what we've managed to show is that this worldsheet theory, under some assumptions, reproduces exactly the spectrum of free n equals to 4 superhang mills in 4 dimensions. So this is the sort of the first step towards finding the concrete worldsheet theory that's due to free superhang mills in 4 dimensions. And this is obviously a vaguely important step forward, because if we can tidy this up, this will allow us to prove the AdS CFT correspondence for AdS5 cross S5. We've written down a worldsheet theory, we can basically solve it, and that should reproduce exactly everything we know about n equals to 4 superhang mills. And if you can prove it, then you have basically proven the AdS CFT correspondence for the case involving 4-dimensional gauge theory. So we are quite excited about it. We believe that's a key step forward to really proving AdS CFT, but obviously there's a long way to go. So there's many things we haven't understood. In the 3-dimensional case, I think we've understood most of it, although clearly we should be able to do better. The 5-dimensional case, there are even more questions, but I think this is probably the most promising route at the moment to see how one can try to prove AdS CFT. So my time is up, so I'll stop here. Thank you very much.
Any questions or comments?
So, you can kind of prove that then out of this that it's a delta function and compute the coefficients,
yes.
or
Well, the coefficient we can't yet compute. We can only show that it's a delta function. But we can't compute it. So I mean, I said it should be the sum of a delta function with this conformal factor. Then the delta function, the conformal factor, should reproduce the conformal factor from the Lunin-Matur covering space construction of the symmetric orbifold. That factor we haven't yet. I mean, these techniques are good enough to tell you sort of the support, but they're not good enough to tell you the coefficient.
But then you could use a Knižník-Samolotchikov equation to find the coefficients.
Absolutely. Yeah. So you can try using Knižník-Samolotchikov conformal bootstrap to work out the exact coefficients. And I mean, look, it would be bizarre if that wasn't. I mean, it basically has to be the right coefficient, because that coefficient is also fixed by bootstrap. So it's almost certainly going to work. But that we haven't yet done. We've seen that it has the right structure. We haven't computed all the coefficients.
Because you know the coefficients from the other side.
Yes.
Yes.
Yes. You know the coefficients from the other side, and you know it's basically fixed by self-consistency. So there isn't really much room for these coefficients.
Okay. More questions? So you're saying that this worldsheet for AdS 5 process 5, so that's going to be still those symplectic bosons?
Well, twice as many. Yeah. So basically the twistor space for AdS 5. So here we have psi plus minus and eta plus minus. So there are 4 symplectic bosons, and we just double them. We add another 4. So we call them lambda dagger and mu dagger. So there are 4 plus 4. And then we have 4 plus 4 fermions. They give you the SU form. And what you see easily is that instead of PSU 1,1/2, out of this construction, you get PSU 2,2/4. Just like we had, like in the exercise yesterday, you saw PSU 1,1/2 level 1, and the AdS5 theory basically gives you PSU 2,2/4. But PSU 2,2/4 is the global symmetry of n equals to 4 superhang mills. So it's a superconformal symmetry of the zero modes.
Still level 1.
You still get it at level 1. Again, it has the same sort of structure as regards the constraintness of the representation theory. It's as constrained as before. You have spectral flow, and then you have identities very, very similar to that. I mean, the localization argument goes through. It's just a little bit more complicated because you see the target space is now a 4-dimensional space, so somehow you have to understand what's the correct analog of what's the covering map, right? The covering map is now mapped from a worldsheet to a 4D space. So So we are still struggling a little bit of exactly understanding how to interpret it, but the structure is very, very similar. And what we've managed to do is we've calculated the physical spectrum of that worldsheet theory, and it reproduces exactly that of free n equals to 4 supermills, the entire single trace perturbative spectrum of n equals to 4 supermills. So that's, I think, already a big step forward. I mean, people have tried this before. So there's actually, our theory looks very similar to a theory Berkowitz proposed some years ago, except he didn't have spectral flow in the additional fields and so on. But they never got the spectrum of n equals to 4. Whereas in our way, there's a very natural way of getting the spectrum of n equals to 4. So we feel that's on the right track. It's the natural generalization of AdS3. And these incidence relations sound very much like the twistor space description of n equals to 4 supermills.
Okay, well, that sounds very exciting. Any more questions? Okay then, Matthias, thanks again.